This video is about derivatives for position, velocity, and acceleration. For our notes, we'll say let s of t be a position function. Position is sometimes also known as displacement. Then v of t equals s prime of t. Okay, so v of t would be velocity, and of course s prime would be derivative of s, meaning here that the velocity is the derivative of the position function. And a of t is the derivative of the velocity function. Okay, so a of t would be acceleration. And if you're familiar at all with any kind of physics or science context in which movement or motion happens, velocity is a very commonly used term, and so is acceleration. Velocity is speed and direction. Acceleration is how fast that is changing. And so you'll see those come to life with some examples coming up here shortly. Let's consider an example which says, suppose a particle moves according to the following function, s of t, so here's our position function, equals, it's a rational function where the numerator is 9t and the denominator is t squared plus 9. Given that, we want to find several things. First, we want to find its velocity after 1 second. Well, you'll recall from the notes above that velocity, which we will call v of t, is really just s prime of t, that is the derivative of the position function, which was given in this problem. Now, this position function was a rational, or is a rational function, which means to take its derivative, we have to use the quotient rule. And so here we go, using our rules that we now know with derivatives. We can say low, which is t squared plus 9, d high, which would be 9, minus high, which is 9t, d low, which would be 2t. And that's all over low squared, which of course is 2t plus 9 squared. Let's simplify this result a little bit here. And in this numerator, distribute the 9 and then multiply the second term together here. So we'll have 9t squared plus 81 minus 18t squared for the numerator. And that's all over the denominator, which we'll just keep for now as t squared plus 9 all squared. All right, if we take this even a step further, in the numerator, we can combine the 9t squared with the negative 18t squared, and altogether we'll leave the 81 up there, but then say 81 minus 9t squared. That's negative 9t squared from combining those two terms. And again, that's all over t squared plus 9 all squared. So this result is the general v of t, the derivative of the position, known as velocity here. But this question was asking for its velocity after 1 second. In other words, we really want to know what v of 1 is. Well, if we know v of t, then we'll just plug in 1 for t, which would give us 81 minus 9 times 1 squared, all over 1 squared, which is 1, plus 9 squared. Okay, so this is really 81 minus 9, which is 72, over 1 plus 9, which is 10 squared, which is 100. So 72 over 100. Now you could keep it as is or reduce it a fraction, or sometimes in a science kind of context you might see it written as a decimal, so you might say 0.72. And now the units matter for velocity. This could be written in this context as feet per second. In this problem where it started, I forgot to mention that s is in feet. That would have to be given in the problem somehow. And so that's why I could say feet per second. Of course, time was given as seconds in the problem, but feet per second wouldn't be obvious unless you were given the units, which I just forgot to write in the problem here, but we're going to assume it was in feet. Related to this same scenario is our next question, which is, when is the particle at rest? Now, given our measurements of position and velocity and acceleration in this context, at rest means it's not moving, which would mean the velocity should be 0. So we could say at rest means v of t should equal 0. Now, we already found what v of t is, and so let's go ahead and bring that back into the scene here from our previous step here. We said v of t was 81 minus 9t squared over t squared plus 9 all squared. So that's our general expression for velocity that we had found using our derivative. If we want to set that equal to 0, then we would just say 0 equals 81 minus 9t squared over t squared plus 9 all squared. But if a fraction equals 0, that's equivalent to its numerator being 0. So we could say this really means 0 equals 81 minus 9t squared. You could also cross multiply in that previous step if you like, but ultimately you're going to get this. And then of course if you just add 9t squared to both sides, you'll end up with 9t squared equals 81. If we divide both sides by 9, then we get t squared equals 9. Now if we take the square root of both sides of this to get t, technically we would get plus or minus 3, but in this context we also should say that time is positive only. Since time is positive, then we would say, to answer this question, t equals positive 3 seconds. So when is the particle at rest? At 3 seconds is when it would hit rest. Thirdly, we could also ask, again using the same function as given above, when is the particle moving in a positive direction? Okay, so remember we said velocity really does mean speed and direction. Sometimes people assume it's only speed, but it actually does have direction as well. Well, positive direction would simply mean then v of t is positive or greater than 0. Now again, we already have v of t, so we'll go ahead and bring that expression back into the view here and say that negative 9t squared, actually we had written 81 first, so 81 minus 9t squared over t squared plus 9 all squared. We want to know when is that positive. That's what it means for velocity to be positive, which would mean the particle is moving in a positive direction. Now, if you take a look at this, there's probably a few different ways you could approach it. It's really just a rational inequality, which is a combination, in this case, of some polynomial inequalities. And so this is a topic going back to algebra. We'll just kind of survey the basics of it here for a moment. We know that in this expression, notice that the denominator, which is t squared plus 9 all squared, that is always going to be positive. No matter what you put in for t, when you square it for the t squared, you'll get something positive. Add 9 to it and it's still positive, and then square that result and it's still positive. So you're guaranteed to get something positive in the denominator of this velocity expression, which means the only thing that could impact whether the entire velocity is positive or negative would be the numerator. And so if this is guaranteed positive in the denominator, and we want an overall positive direction, of course, our question then is, when is the numerator positive? Because a positive over a positive would indeed be positive. Okay, so we're kind of translating this into a simpler problem, which is, when is 81 minus 9t squared, that's the numerator, when is that positive or greater than 0? And then this we can solve. Let's add 9t squared to both sides, which will give us 81 is greater than 9t squared. You could divide both sides by 9 here using the old inequality steps here. That's a positive value, so we don't have to flip the inequality symbol at all. 81 over 9 on the left side is really just 9. So our question is, when is 9 greater than t squared? And there are a couple different ways you could solve this. It turns out it would be the case when t is somewhere between 0 and 3. Let's dig into this a little bit more to make sure we understand fully how these boundaries work. If I were to pull out a graph of t squared, which is really the function part in this inequality we have here. Remember, t squared is like a parabola, and you've been working with these for a while. It looks something like that. Now we want to know, when is t squared less than 9? So that'd be like putting 9 on the y-axis and then saying, well, where and how and when does this parabola occur that's less than that, which would be anything below 9. Of course, as you know from algebra, when t in this case is 3 squared is 9, so there's one of the boundaries. But then when t is negative 3, that would also give us an output of 9 for this t squared function, which means we care about when t is somewhere between negative 3 and 3. But as we've already stated, t has to be positive, which is why we really wouldn't be able to say that t is somewhere between negative 3 and positive 3, because it doesn't actually go less than 0. So what we're going to have to say is 0 is the lowest boundary, but t actually could be 0. So we'll say t is greater than or equal to 0, but less than 3, to give us the values of t where this particle is moving in a positive direction, which again is where the velocity would be positive. Let's try a fourth question in this context. Same problem, same position function from above. This one says find the total distance traveled during the first 6 seconds of this particle moving. Okay, so let's bring in a couple key things. First of all, we'll say this: total distance is going to be equal to the absolute value of the end minus the beginning. That's just kind of a true fact that goes all the way back to algebra. If you go back even to the distance formula, you will find this kind of understanding embedded within it. So that's just how we understand total distance in a sequential context where you're starting somewhere and moving along something. So the end minus the beginning will be the total distance. Of course, we make it the absolute value to ensure that it's positive. But there's an extra twist in this problem, which is, if you think of the timeline of travel here, so we start at 0, and this problem says the first 6 seconds. Well, we've already analyzed this problem enough to know that something significant happens at the 3-second mark. If you go back and recall, the velocity function at 3 seconds, between 0 and 3 seconds is positive. And we found that algebraically in a previous step. That's what we already know. It's positive from 0 to 3, which means it must be negative from 3 to 6. If we found anywhere it's positive in the previous step and came out with 0 to 3, that was where that function is positive, then anywhere else it should be negative, which would include then 3 to 6. Well, the reason that matters in this next question is because if you're talking about the total distance traveled, the direction you're going matters. So if you have velocity that's negative, then the direction is changing, and that calculation may actually cancel out some of the positive direction positional change that's happening. So to account for this, all we have to do is make sure that our total distance, we'll call it d for distance, cuts the interval into these two different pieces. So from 0 to 3, we want to find our distance as, okay, using again this end minus the beginning general understanding of distance, we'll say s for position of 3. S of 3 is the kind of like the end of the first interval minus s of 0, which would be the beginning of the first interval. But then we want to add that distance to the distance we get from the second interval, which in the same way would be s of 6, the end of that interval, minus s of 3, the beginning of that interval. Now, if these values end up positive already, then the absolute value doesn't really do much for us, but this will ensure that our values do end up in the right context, which is distance should be positive here. Now, if you plug this all in, we should end up getting 3/2 for the first. I'm just skipping a step or two here, and then 3/10 for the second interval. Of course, if you just add those using a common denominator, we'll get 9/5, which you could turn into a nice clean decimal as 1.8. And then distance would go in according with the units of this problem, which way above we gave as feet. So we could say 1.8 feet for this. Fifthly, in this same context, we now want to find the acceleration after 1 second. Now, we've already discussed above that acceleration is related to position and velocity, and so a of t for acceleration we said is v prime of t. It's the derivative of the velocity. And the velocity, which we have written above, you can go back and look at that or glance at it. It's a rational function, which means we're going to have to use the quotient rule to take its derivative. And so if we write that out, of course, we know that's low d high. Well, for that velocity function, that would be t squared plus 9 squared, there's low, times d high would be negative 18t. There's low d high minus high, which is our 81 minus 9t squared. So we have low d high minus high d low. And now the low, that was the t squared plus 9 all squared. If I use the power rule and chain rule for that, the d low really should be 2 times t squared plus 9 times the derivative of that inner piece, which would be 2t. And that's all over low squared, which would now be t squared plus 9 to the 4th, since we're squaring that binomial, which was already squared before. Okay, so it's a little ugly. We're not actually going to go too much further as far as cleaning up the algebra of this, because we actually have our input given. We want to find this acceleration at 1 second, which means we really just care about a of 1. So why simplify all the algebra if we're just going to plug in 1 for t's anyway? So if I say a of 1, but now plug in 1 for all these t's, we should end up with 100 times negative 18 minus 72 times 2 times 10 times 2. Okay, so again, all these factors and terms in this step are associated with the previous step that we got for all the algebraic terms of the velocity derivative, but I'm plugging in 1 for t, and then of course same thing in the denominator, that would turn out to be 10 to the 4th. And so this, if you crunch this out, maybe with the help of a little calculator, I think you'll end up with negative 0.468. And then the units are always important. For acceleration, we're going to use feet per second squared. It was feet for the units of distance, as stated above. Feet per second would be the units for velocity, and then feet per second squared would be the units for acceleration. Let's try another example. This one states, if a ball is thrown vertically upward with a velocity of 80 feet per second, then its height after t seconds is given as this equation, s equals 80t minus 16t squared. So it says s, you could also think of that as s of t. The point is that's our position function. Now the first question says, what is the maximum height reached by the ball? Okay, well, sometimes a picture can be helpful, just to kind of organize the algebra here. So let's imagine a ball being thrown upward, it finally kind of hits its max, and then of course gravity pulls it all the way back down, and eventually it'll hit the ground. What we care about is, what is this max height, at least for this question here? Notice though that at that particular moment, when it's reached the max height, though it be a very, very, very small sliver of time, the ball actually stands still there. And so that would be where we find the max height. So it's just kind of frozen at the top. Of course, you can't even really probably tell with the human eye where that occurs, but it pauses for a brief second, then starts coming back down. At that still moment, that's when we could say that the velocity of v of t would have to be 0. Now recall that velocity, v of t, as we defined way above in our notes is really s prime of t. It's the derivative of the position function, which in this problem was given as 80t minus 16t squared. So the derivative of that would simply be 80 minus 32t. That's just using the basic polynomial derivative rules we know at this point. And if that's our velocity, we simply want to set that equal to 0. So we'll say 0 equals 80 minus 32t. And then, of course, that means 32t equals 80. And, okay, solve this a step or two further, and I think you're going to end up with t equal to 2.5. or 5/2. Now let's be clear, this is the time when the ball stands still. Okay, that's all we've found so far. After 2.5 seconds, the ball reaches that max height, and we know it's the max height because the velocity stands still briefly there. And so we can say that after 2.5 seconds it reached the max height, but that's not quite the question being asked here. The question is, what is the max height, not when does it occur? So now to go back and find the actual max height, that'd be like plugging in the time of 2.5, which we just found, to tell us when this max height occurs. But where it is, or what is that max height, would be a position kind of question. So that's an S of 2.5 kind of question, and our S function is written above. If you plug that in and crunch it out, I believe you should get 100 feet for the actual max height of this ball. Secondly, within this same context or example here, we want to ask this: what is the velocity of the ball when it is 96 feet above the ground on its way up, and then of course also on its way down? Okay, so let's get the context. I think a picture is usually pretty helpful for this. Remember, the ball's kind of going up, peaks out, and then it comes back down. We also just found that this maximum height reached by the ball turned out to be 100 feet. Now in this question, they're asking, what is the velocity of the ball when it is 96 feet above the ground? So 96, of course, would be a little bit below the max, but notice that it would occur in two places. It'd be on the way up and then on the way back down. It would cross the 96 feet height level in both of those directions. Now, the question is, what is the velocity when it is 96 feet above the ground? Well, we have a velocity equation, v of t, above, but notice that you have to know the time to plug into velocity to get the actual value, which means what we really want to know is, when does the ball actually hit those two places? If I know these t values, I can simply plug them in the velocity equation and then get the velocity in both cases, on the way up and on the way down, which is what this question is asking. Okay, well, I'm not going to get these t values unless I go back and use our position equation. So let's recall that given above in the problem, S of t was 80t minus 16t squared. So what we really want to know is, when does that position, the S of t function, when does it actually hit 96? Right? That's what this question is focused on. So we're going to set 96 as the value of the position, and that of course will equal 80t minus 16t squared. And now we're going to solve this. This is now just some algebraic quadratic equation solving here. We could get everything on one side, which would mean negative 16t squared plus 80t minus 96 would equal 0. We could do a little algebra with this one. If we factor it out a negative 16, we'd be left with a t squared minus 5t plus 6. It's all equal to 0. Keep this going. We could factor then this trinomial and get a t minus 3 and then a t minus 2, which tells us two things. As you know from algebra, this would tell us t could be 3 or t could be 2. Now in context, this is making some sense. Remember, we're expecting the ball to hit this height of 96 feet 2 times, on the way up and the way down. Well, what this tells us after solving this quadratic is that the first time must be the 2 and the second time must be the 3. Just going in sequential order, right? So those are the times when the ball hits that. This question, though, said, what is the velocity at those? Well, then we go back to our v equation above. We want to know what v of 2 is, and we want to know what v of 3 is. Those will give us the velocities at these two times, which is when the ball will be at this height of 96, which we know from tying all these equations together. Okay, it turns out v of 2, if you plug 2 in for the velocity equation above, we get 16, and that'd be feet per second. And then when time is 3, v of 3 would give us negative 16 feet per second. The symmetry is making some sense here. And this, of course, the first one is on the way up, and the second one's on the way down. And so those are the two velocities that were being asked in this problem. Notice how all these equations that we've been studying in this video here, the acceleration, velocity, and position, clearly they're all related in that you use derivatives to go from one to the next. But notice how in problem solving with them, you also have to understand not just how to find a derivative, but what is making sense, like which equation needs to be used. In this particular problem, we used a couple different equations, and so tying them all together is also very important.